All right, now let's do a little bit harder round of problems. Let's do some water potential problems. Well, now we also have to solve for the solute potential. So solute potential, this is straight from the formula sheet as well. It's just that second half of the water potential section. So we can see here, solute potential, remember that's psi sub s, is equal to negative I CRT. And it tells you what all those things are. So I is the ionization constant. It's whenever that solute is dissolved in water, how many solutes will it dissolve into? So for example, for sucrose, and it tells you this here, when you put sucrose in water, it dissolves and it stays sucrose. It just is. But if you took something like sodium chloride in water, table salt, it actually will dissolve into sodium ions and chloride ions. So the ionization constant for that would be 2. You don't need to know solubilization rules or like ionization rules for AP Bio. The questions will tell you if the ionization constant is something other than 1. In most problems, it's going to be sucrose, which I just equals 1. But if not, the problem will say. Okay, so that's negative I. C, that's the concentration of your solution in molar. R is a constant that will always be given to you. It's on this formula sheet. And then T is the temperature of the solution in Kelvin. Crucially, in Kelvin. Don't forget to convert to Kelvin, right? So we can tell by looking at this formula, this is why the solute potential of pure water is 0 bars. Because what's the concentration of solutes in pure water? Well, it's 0. There are no solutes, right? It's just water. So if we plugged 0 into this formula, we would get 0. Makes sense, right? Looking at this, we can also understand that as we add more solutes to a solution, the solute potential is going to get more negative. It's going to decrease, right? Because of this negative sign right here. Don't forget that negative sign. It's so crucial. So if we have a really concentrated solution, it's going to have a really, really, really negative solute potential. And so because of that negative sign, that's why solute potential can only be 0 or negative. If you're doing a problem and you get a positive solute potential, you did something wrong. And one way I like to think about this is, remember, water is going to move towards solutes most of the time, right? So you can think that the solutes are almost like sucking the water towards them. So you can think of water getting sucked towards those solutes. So solutes are almost making like a negative pressure that's sucking water towards them like a vacuum. Okay, let's do some practice problems. All right, first one. Calculate the solute potential of a 0.35 molar sucrose solution at 25 degrees Celsius. Okay, so for this, we're just going to go ahead and use, this is the same little formula that was on the previous slide. We're just going to use this down here. So what is our formula for solute potential? It's solute potential equals negative I CRT, and then we're just going to plug into the formula. So negative doesn't tell us what I is, so we better check what it's written here. It says I equals 1 for sucrose, and this question's talking about sucrose. So 1, and then C is the concentration in molar, so that's just going to be 0.35 molar. R is always this constant, it's always the same. I'm not going to write all the units on this constant because it's long, and I'm running out of space. And then last T, temperature, and remember temperature has to be in Kelvin, so don't forget to add that 273. So it'll be 25 plus 273. Okay, and then we are going to go ahead and just plug that into our calculator. Okay, so we plug all of that in, and we get, don't forget the negative sign, right? Negative 8.67. And what's the units? The units is always going to be bars. We could check our units and they'd cancel out, and all we would get left here is bars. Okay, and there is our answer. I rounded to the hundredths place. That's usually a good rule of thumb. If you round to the hundredths place, you generally will never get in trouble with like rounding errors. Okay, let's try another one. Calculate the solute potential of a 0.1 molar NaCl solution at 22 degrees Celsius, and it tells you that NaCl has an ionization constant of I equals 2. Okay, so let's go ahead and do this one. So we're going to do the same thing. We're going to use this solute potential formula. and we are just going to plug and chug. So solute potential is negative ICRT. And in this case, I is equal to 2, right? So negative 2. What's C? It's the concentration, so that's 0.1. And then R, always the same number, always that constant. And then T, don't forget to do the temperature in Kelvin, not in Celsius, so 22 plus 273. All right, let me plug all that into my handy dandy calculator. All right, we get 4.90. And don't forget the negative sign, right? Negative 4.90. And what's the units? It's always bars. Bars. Okay, there we go. So now that we've gotten some practice calculating solute potential, let's do the hardest problem of all. We got to combine everything into one massive problem. All right, so the value for solute potential in root tissue was found to be negative 3.3 bars. If you place the root tissue in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the solute potential of the solution, and in which direction would the net flow of water be? So what's the first thing we should do? Draw a picture. That's right. So I'm going to just draw my little picture. Here's my beaker. Here's my root. The problem tells us that the solute potential, so it's given us just the whole thing, makes our lives easy, right? The solute potential in that root is a negative 3.3. So I'm just going to write that in here, negative 3.3. And now we need to calculate the solute potential of the solution outside. So for the solution, to calculate that, it tells us, well, I'll do this. This equals, so water potential is the pressure potential plus the solute potential. But it tells us it's in an open beaker, right? That means that this water potential is going to equal 0. So in other words, the pressure potential. In other words, the water potential is just going to be the solute potential because this equals 0. Okay, so we just got to solve for the solute potential. So solute potential is negative ICRT. So let's just go ahead and plug all that in there. It's sucrose, so I is going to be equal to 1. Negative 1. And the concentration is 0.1 and 0.0831 times 20 plus 273. Okay, let's plug that into our calculator and see what we get. So we get 2.43, but don't forget the negative, right? Don't forget that negative. Negative 2.43 bars. Okay, so that's the first part of the problem. So let's go ahead and put that information onto our picture. So negative 2.43. Okay, now it's really easy for us to compare those two numbers and just draw an arrow. So because we're talking about water potential, the arrow is always going to go from the greater to the lesser, the more negative number. So which way is the arrow going to go? It's going to go into the cell. Water is going to go into the cell. So water moves into the cell. And there we go. That's pretty much as tough as those questions get. And it was a lot of steps, but it's not horrible, right? We did it. And that's how you do water potential.